Hi everyone and welcome to another math revision with Jov. Today we're actually going to be proving this statement. It says let p be some prime and prove that the square root of p is irrational. You've probably seen a similar proof for proving that the square root of 2 is irrational, but this is a more general case. This is one of my favourite simple proofs, I suppose. And why is it so nice and why is it so simple? Well, it relies on the fact that if you take some p squared, some prime p squared, and we say that that divides some number k, then that implies that p divides k. And that's one of the facts that we're going to be relying on. So where do we start with this? Well, we want to assume the opposite, and then we want to lead to a contradiction. We call this proof by contradiction. So how would we do that? Well, we want to set up the negative statement. So we want to say, suppose that the square root of p is rational. So suppose that the square root of p is equal to some rational a over b, where a divided by b is in its simplest form. So we cannot divide a and b by the same number and get another integer in both cases, and that's the same as saying that the greatest common divisor of a and b is 1, the highest common factor, if you will. So we can go ahead and manipulate this equation around. We say that p is equal to, well, I've squared both sides, so that's a squared divided by b squared, and then we get that a squared is in fact equal to p times b squared. And that means that a squared is actually a multiple of p, okay? So a squared is a multiple of p, which that means that p divides a squared, which means that p divides a. Oh, sorry, when I said this earlier, I said this a little bit wrong. What I meant was when p divides k squared, p divides k. Okay, that's cleared up. So yeah, what I've done here is I've said that p divides a squared. So for some square number that is a multiple of a prime number p, that prime number must also divide whatever the number that I've squared was, and that is a common fact in number theory. Now, what this means is that there exists some c, so there is some c such that a equals p times c. So there is some c, some integer c, such that when we multiply it by this number p, we get a, and that's the same as saying that p is a divisor of a. So we can go ahead and use this little set of equations here and say that, well, a squared is just pc all squared, and that's equal to pb squared. So p squared c squared equals pb squared, and since p is not equal to 0 because then it wouldn't be prime, pc squared equals b squared. And what that means is that p is a divisor of b squared, because b squared is a multiple of p over here. And that means that p divides b. Okay, great. So where is the problem in this? Well, the problem lies here, where I've said that the greatest common divisor of a and b is 1. However, we've got this statement here and this statement here, so that p divides a and p divides b, which means that a and b cannot be in its simplest form. And that is the key here. That is where the contradiction is. So we have reached a contradiction. We have reached a contradiction. And when we reach a contradiction, that means that our initial statement, our initial assumption was false, which our initial assumption was this. This must be false, so P is not equal to some rational number, which means that the square root of P is irrational. Great. And that is the end of our proof. So I'll get to draw my little square that means the proof is finished. And yeah, that's it.